Touch a refrigerator magnet to a box of screws labeled stainless steel. Some of them will jump to it. That reaction tells you something real, and it also produces false alarms on perfectly good screws, and almost nobody in that aisle knows how to tell those two cases apart. We went through Fastener Industry Technical Guidance, a Department of Energy manual on counterfeit parts, and the metallurgy of how a screw is formed. One federal audit of its own supply rooms turned up 159 stainless fasteners carrying grade marks that had been stamped on by hand. Those parts cleared a full procurement system on their way in. The switch away from that alloy happened for a reason. Nobody printed on a box, and it comes down to how hard a screw must be to drill its own hole. We are covering what changed, what the magnet actually proves, and the two checks that hold up. 6 bins sit on the fastener aisle, every one of them labeled stainless steel, and the prices across them vary by a factor of 4. Nothing on the front of those boxes explains the spread. Stainless is not one metal. It is a family of alloys sharing a minimum chromium content, and the members behave so differently outdoors that treating them as interchangeable is how decks end up streaked with rust after 2 winters. The austenitic grades carry chromium and nickel together. That combination resists corrosion extremely well and leaves the metal comparatively soft. These are the 300 series alloys, and they cover most of what a homeowner should be buying. The martensitic grades sit in the 400 series, built around higher carbon with almost no nickel. They can be hardened by heat treatment, they hold an edge under load, and they trade away a significant share of their corrosion resistance to get there. Ferritic grades occupy a middle position, magnetic like the martensitics, common in appliances and exhaust systems. 4 grade numbers matter once you are standing in that aisle. Types 302, 304, and 305 make up what the trade calls 18 to 8, named for roughly 18% chromium and 8% nickel. Their corrosion properties are close enough to treat as equivalent. Type 305 exists for a specific manufacturing reason. It was developed to improve the cold heading qualities of 18 to 8, meaning it forms into screw heads without cracking or galling during production, which is exactly why deck screws end up made from it. Type 316 adds molybdenum. That single addition is what makes it the grade specified around saltwater, pool chemistry, and coastal air. Type 410 is the hard one. 11 to 13% chromium, no nickel at all, heat treatable, cheaper. The difference shows up in ways you can see. The 18 to 8 grades may pit and discolor in saltwater or other high chloride atmospheres, and when they do, the color bleeds through finishes and streaks the wood surrounding the fastener. That brown weeping down a cedar board is the screw failing in public. With 410, the problem runs deeper than appearance. The 400 series alloys are vulnerable to hydrogen-assisted stress, corrosion, cracking, and prolonged exposure to harsher conditions can develop harmful rust that weakens the connection itself. Every bin on that aisle can legally use the word stainless. The corrosion performance between the best and worst of them varies by considerably more than the price does. Which raises the obvious question about the magnet in your kitchen drawer and whether it can sort any of this out. A magnet works because of how atoms arrange themselves inside an alloy, and stainless comes in arrangements that differ from one another. In bar stock or sheet, 304 and 316 are non-magnetic, while martensitic grades like 410 and 420 are magnetic by nature. Testing raw material with a magnet is straightforward, and it gives an honest answer. A screw is not raw material. Screws are not cast in molds. They are formed by force. A wire blank gets driven into a die to shape the head, then rolled between hardened plates to cut the threads. Both operations push enormous stress into the metal, and that stress rearranges part of the crystal structure of austenitic stainless. The chemistry of the alloy does not change by a single percentage point, and the screw starts answering to a magnet anyway. The effect is strongest when cold forming smaller items, which means screws and nails specifically. Fastener distributors live with the consequences. A customer opens a box, jams a refrigerator magnet in, watches the screws stick, and calls convinced the order was wrong. Type 316 and Type 305 generally do not develop those magnetic properties because their higher nickel content holds the structure stable through forming. That asymmetry is what saves the test, and it turns a yes or no question into 3 separate readings. A screw that slams onto the magnet and grips hard points toward 410 or toward plain carbon steel wearing a bright finish. A screw with a faint, weak pull is entirely consistent with genuine 304 that has been through a forming press. Weak attraction is not evidence of fraud. A screw showing no attraction at all after being headed and threaded is a strong indication of 305 or 316, the 2 grades most worth having outdoors. One limitation belongs in the open, because anyone in the trade will raise it within about 10 seconds. Professional buyers are advised to stop using magnets for incoming inspection altogether and to demand test reports or chemical analysis of the alloy instead. A magnet sorts probabilities. Nobody should treat it as identification, and a roofing contractor who does will eventually pay for it. Standing in a hardware aisle with no laboratory nearby, sorting probabilities is worth considerably more than guessing. What the magnet cannot explain is how the harder, weaker alloy ended up filling so many of those boxes. That story starts with a chemistry problem nobody in the industry has ever been able to engineer around. The self-drilling screw rewrote how buildings go together. 1 motion instead of 3. No pilot hole, no bit change, no drop drill on a ladder. Roofing, cladding, steel framing, curtain wall, entire trades reorganized around fasteners that cut their own way in. That convenience carries a physical requirement. The point of the screw has to be harder than the steel it is cutting. Austenitic stainless cannot deliver that, and the reason sits in the same number that makes it corrosion resistant. Carbon content in 300 series stainless runs below 0.08%. Carbon is what allows steel to be hardened. Heat it, quench it, and the carbon locks the crystal structure into something brittle and hard. Strip the carbon out, and that mechanism disappears. The alloy stays tough, stays ductile, and stays soft no matter what you do to it in a furnace. Fastener manufacturers state the consequence plainly in their own literature. Stainless self-drilling screws are made from 304 or 316 grades. Those grades cannot be hardened, and the drill point can therefore only cut into softer materials like aluminum. They also flag the assumption that costs people money on job sites. It is a common error to believe that a stainless self-drilling screw will drill into steel. It will not. The point deforms, the flutes clog, the screw work hardens the hole it is failing to make, and eventually the head twists off. For manufacturers, the constraint was absolute. Making drill points hard enough to cut steel meant making them out of steel carbon steel, heat-treated, with everything that implies about rust. So the industry arrived at a fork with no comfortable branch. Corrosion resistance and hardness are governed by the same element in opposite directions, and no amount of process engineering moves that boundary. Installation speed won, and it is worth being fair about why. A contractor fastening a metal roof is not indifferent to corrosion. He is choosing between a fastener that installs in 2 seconds and one that requires a pilot hole on a job priced by the square. Multiply that across a crew and a season, and the arithmetic stops being close. None of that was a shortcut or a swindle. It was a real limit in the periodic table, met by a market that valued speed. And the honest verdict on this stretch of the story is that the engineering was sound. The cost cutting came afterward, in what got sold to fill the gap. The gap left by that constraint got filled two ways, and one of them is genuinely correct engineering. Type 410 moved in first. Heat-treatable, strong, cheap, and carrying enough chromium to earn the stainless label without the nickel that drives up cost. In masonry anchors, it is the right answer. Concrete screws and tapcons come in 410 because driving into concrete without snapping demands hardness above everything else, and an anchor inside a wall cavity is not swimming in chlorides. Roofing screws and self-drillers followed the same logic. Coated carbon steel took the other route. Harden the steel, then wrap it in something to keep water off. That approach works until the coating stops being continuous, which happens the first time a driver bit slips off the head or a screw scrapes through a metal flashing on its way in. Both compromises get sold in bins marked stainless steel, next to each other, to people buying screws for a coastal deck. Then the industry built the thing that actually solves it. Bi-metal screws weld two different alloys into one fastener. The drill point and the first tapping threads are hardened carbon steel. Everything behind them, the shank, the remaining threads, the head is 304 stainless. The hard tip cuts the hole and forms the thread, and the stainless body follows it in and stays there for the next 30 years. Manufacturers describe the sequence as 3 operations happening in one motion. The screw drills, it shapes the thread, it tightens. Some are rated to cut through steel up to ½ an inch thick. Consider what it took to get there. 2 separate metals joined by a weld inside a fastener the size of your finger, produced at industrial volume because a single alloy could not do both jobs. Nobody engineers a 2-metal screw for fun. That product exists as a direct admission of the limit described a minute ago. Bi-metal fasteners are specified by name, sold through suppliers rather than in shelf bins, and cost more than either alternative. They are also the reason a metal building can be fastened quickly and still be intact after 2 decades near the ocean. So the alloy question has a clear answer, traceable through published metallurgy and product catalogs. The marking question does not. Once a screw has been formed, hardened, and finished, what it claims to be comes down to a stamp on the head, and that is where this stops being metallurgy and becomes fraud. A stainless fastener carries information stamped into its head. 2 marks are supposed to be there, one identifying the grade of the alloy, one identifying the company that made it. The 18-8 convention is 2 radial lines set 90 degrees apart. Other marks a buyer might encounter include 18-8 spelled out 304 or F593C. A shop stock inspection at one federal site turned up bolts carrying all 3 of those raised markings mixed together. Then there is B8, which carries more weight than the others. B8 refers to ASTM, A320 grade. B8, a specification for bolting in demanding service, with defined requirements for chemistry, heat treatment, and testing. A genuine B8 bolt has been through an upgrading process and certification testing. That process costs money, and the cost is exactly what makes the stamp worth faking. In November of 1993, the Industrial Fasteners Institute issued a fastener advisory about 18-8 stainless bolts, describing a bait and switch running through the distribution chain. The method required no equipment beyond a punch. A distributor obtains an ordinary 18-8 bolt carrying the 2 radial lines and no manufacturer marking. Somebody hand stamps B8 onto the head. It then sells as ASTM A320 grade B8 without the upgrading process or the certification testing ever happening. Buyers receive bolts that looked correct, were priced correctly, and had been tested by nobody. That fraud does leave a physical trace, and it is the most useful thing in this entire section. Legitimate grade marks are formed during manufacture. When the die shapes the head from a wire blank, metal flows outward into the recesses of the tooling, which leaves those marks standing proud of the surface. Raised. A hand stamp arrives afterward, struck into a finished head with a punch. It sinks into the metal. Depressed. The guidance that came out of the advisory reflects that difference. A bolt discovered with dual headmark stamping, carrying both raised and depressed marks, should be considered suspect. Two marking operations, performed at two different times, by two parties with different intentions. You can run this check in a hardware store with nothing but daylight. Hold the head at an angle so light rakes across it. Marks that were made together at the factory will sit at the same level and share the same crispness. A mark that sits below the surface, next to marks that stand above it, was added later by somebody. That advisory went out more than 30 years ago. What happened when a federal agency went looking through its own supply rooms is the part that should unsettle anyone assuming a large organization would catch this. The advisory prompted the Department of Energy to search its own facility stores. These are national laboratories, weapons sites, nuclear facilities, organizations with procurement departments, quality assurance programs, receiving inspection procedures, and written specifications covering everything down to a washer. Hundreds of stainless steel bolts carrying hand-stamped B 8-grade markings turned up in facility stores throughout the Doe complex, alongside a variety of other raised and depressed head and manufacturer markings. One tally within that search recorded 159 stainless steel fasteners with hand-stamped B 8-grade marks, together with raised or hand-stamped manufacturer symbols. Nobody smuggled those parts through a fence. They arrived on purchase orders from established distributors with paperwork attached and sat on shelves until a technician needed a bolt. At which point, the obvious professional answer surfaces. Forget magnets and head marks entirely and ask for documentation. A mill test report states the measured chemistry of the batch, a fastener, came from chromium, nickel, carbon, molybdenum, each expressed as a percentage against the specification. That document is what the industrial supply chain actually runs on. An engineer described receiving material accompanied by precisely that. The mill certificates listed compositions in accordance with the specification and additionally indicated 100% positive material identification. On-site X-ray testing, later confirmed by a third-party inspection company, found the material several percent under specification in nickel content on 3 of the 4 lengths tested. Consider what several percent means in this context. An 18-8 alloy is named for containing roughly 8% nickel. Nickel is the element that makes austenitic stainless what it is, and it is the most expensive ingredient in the mix. A shortfall of several percentage points is not a rounding error or a bad sample. It is a different material wearing the right label. Falsification of this kind reaches well beyond anonymous suppliers. Employees at Kobe Steel falsified material test certificates so that materials would appear to meet customer specifications when in fact they did not, which leaves the careful buyer somewhere uncomfortable. Magnets misfire on cold-worked stainless, as the physics guarantees they will. Grade marks can be added to a finished head by anyone holding a punch. And certificates, the thing everyone falls back on, are documents printed, signed, and forgeable like any other. The metal itself cannot be edited. An alloy corrodes in salt water according to what is genuinely inside it, indifferent to the stamp on its head, the certificate in the file, and the bin it was sold from. That behavior is measurable on a kitchen counter over 2 days for the price of a box of salt. Fill a bowl with water and stir in salt until no more will dissolve. Drop in 1 screw from each box you are considering, keep them from touching one another, and set the bowl somewhere out of the way for a day or 2. Then look at what came out. Genuine. 304 and 316 emerge looking exactly as they went in. A 410 screw starts showing small brown specks, usually beginning at the thread roots and around the drive recess, where forming stress concentrated the metal. Carbon steel wearing a bright finish often gives itself away within a few hours. The slowness of this test is precisely what makes it valuable. No stamp defeats it, no certificate overrides it, no bin label changes the outcome, because it asks the alloy to behave rather than to make a claim. 2 days and $1 of salt. The magnet gives you the 30-second version, and you can now read it properly. A firm grip suggests 410 or coated carbon steel underneath a finish. A faint pull is entirely consistent with real 304 that has been through a forming press, and it counts as no evidence of anything wrong. Zero attraction on a screw that has already been headed and threaded points toward 305 or 316. Then examine the head under raking light, holding it at an angle so shadows catch in the marks. Every legitimate mark was created in the same instant the head itself was formed, which means they should sit at a consistent height with the same softness at their edges. A grade stamp sunk below the surface alongside raised marks was added afterward by someone with a punch. A grade mark standing alone, with no manufacturer identification anywhere on that head, is reason enough to put the box down. The fourth check happens before you touch anything. Read the listing or the box and look for a number. A seller printing 305, 316, or a 4 has made a specific claim that a specific company can be held to. A seller printing the single word stainless has committed to nothing whatsoever, and that vagueness is usually a choice rather than an oversight. Matching grade to job turns out to be simpler than the metallurgy behind it. Inland outdoor work, decks, fences, railings, gates, calls for 305. Coastal air, pool chemistry, road salt, anything that gets splashed with either. 316, and no negotiating on that one. Reserve 410 for situations where hardness does the work and moisture never arrives, such as masonry anchors in interior walls or concrete screws driven into a dry basement slab. The price step from 305 to 316 reflects nickel and molybdenum content, and both of those elements are genuinely expensive. That premium buys the specific atoms doing the corrosion work. All of which leaves one question from the title still open, and the answer is not what the phrasing implies. Nobody stopped making screws from real stainless steel. Type 305 is sitting on shelves right now, sold by name, and 316 is available to anyone willing to pay for the molybdenum inside it. The standards defining those alloys never softened, and no committee quietly lowered a threshold the way it happened with lead in plumbing brass or with furniture disclosure rules. Buy 316 today and you receive what 316 has always meant. The change happened around those alloys rather than to them. Screws were asked to do a job the good metal cannot perform. Drilling through steel demands hardness. Hardness demands carbon. And carbon is exactly what austenitic stainless leaves out in order to resist rust. Facing that, the market filled its bins with 410 and with coated carbon steel, and the word stainless stretched to cover all of it. What genuinely degraded was the evidence. A hand punch turns an ordinary bolt into a certified one. Certificates get printed with numbers nobody measured. Marking and documentation slipped in a way the metallurgy never did. So, the rule that replaces everything in this video comes down to one habit. Buy the grade in writing. A listing showing 305, 316, or a 4 is a claim attached to a company. A box showing only the word stainless commits nobody to anything, and vagueness at the point of sale is nearly always deliberate. Around that, 4 checks, none of which takes real effort. Run a magnet across anything headed outdoors and read it as a probability rather than a verdict. Put screws in salt water for 2 days before committing them to work you cannot easily undo. Tilt the head under a light and confirm every mark was made in one operation. Confirm the grade before purchase rather than after. One habit costs nothing at all. Put your best grade where replacement is hardest. Under decking, on roofing, behind cladding, anywhere structural. Save the cheaper fastener for the gate hinge you can reach with a screwdriver on a Saturday. Weigh the money honestly. Upgrading an entire deck from mystery stainless to genuine 305 runs, perhaps $40 on a job of that size. Pulling 200 rusted screws out of finished decking 4 years from now with the boards already stained around every hole costs a weekend you will not enjoy. The alloy in your hand does not care what the box said. It corrodes according to what is actually inside it. If this changed how you look at that bin, pass it to whoever is fastening something outdoors this month that they hope never to touch again.